Hello everybody. Today we're focusing on global positioning systems, but which are more commonly known as GPS. And this lecture is really going to focus more on the idea of how the whole system works, as opposed to the use of the actual receiver instrument. So that will be the focus of lab. So for the lecture, we're really focusing on the system as a whole and how it works. One too far. Back that up. There we go. So, a little history of it. So GPS was developed for the military, developed during the Cold War, and basically the space race. So the Russians decide to launch Sputnik in '57, and then there's just this focus of getting into space and space exploration. And so one of the big things that we then focused on was the idea of this GPS system and being able to help with location a lot. So the big focus at first became the U.S. Navy. So in 1960 we had the transit system, which allowed Navy ships to fix their position once an hour. So just think about how it's gone in the 60 years from 1960 to now, in terms of Navy ships had to check their position, or were able to check their position once an hour, whereas you now have a GPS in your phone. You can get a GPS receiver, and it takes seconds to get that information. Transit was replaced by Timation in 1967, which started using atomic clocks, and we'll talk about those a little bit later in the lecture. Oh, I did it again. There we go. So GPS was exclusively used by the military until 1983. The Reagan administration then opened up GPS for civilian use, and that became extremely important for natural resources, because it's something that has become a really useful tool for natural resources now that it's not the military use only. I always do like to think about what else is out there, because I'm sure the military has come up with a better system since then, and I always kind of wonder what will GPS look like in 10 years or so. GPS originally was about 11 satellites, but then with the new system, the network that's been set up now, you need a minimum of 24 satellites, and currently there's 31 active satellites in the GPS constellation. And so if we take a look at just kind of the development, so there were 13 satellites launched between 1997 and 2004, 8 satellites launched between 2005 and 2009, 12 satellites between 2010 and 2016, 10 satellites are under contract, and they're getting ready to go. So the big thing here is to just understand and see there are some slight differences between the satellites. I'm not going to expect you guys to know all that. I'm just trying to give you a basic history of it, and really more of trying to paint the picture that it is so much more complex, and there's so much that goes into it, more than just the idea of there's something in space that beams a signal to this thing in my hand. There's a lot that goes into figuring it out. And so let's look at where we're at today with GPS. Kind of myself out of Colorado real quick. So the U.S. GPS system is managed by the Air Force, the 50th Space Wing at the Schriever Air Force Base in Colorado Springs, Colorado. One of the reasons for it being in Colorado Springs, Colorado, is its high plains. So as you can see by this picture here on the right of the GPS facility, it's nice and high above everything else, but also flat, so there's not a lot of things that can interfere with the system. Navstar is the system that GPS falls under, is really expensive, $1.2 million of maintenance every year, and that's because if you're managing 31 satellites and all that goes into them and creating satellites and doing all that, it gets expensive. The original accuracy was limited to 100 meters, but in 2000, Clinton turned off that selective availability, and now you can get down to about a meter, or, you know, it kind of depends on what other sources of errors you have, but you can get pretty accurate information these days. So, what kind of systems are there out there? All sorts of things. Mostly they're used for navigations. We have them in our phones or our tablets or our cars, also handheld systems. Mostly in natural resources, it's handheld receivers. Some people just use GPS to have fun. So there's geocaching, which the video for your lab will discuss a little bit, but just the idea of people hiding stuff and then you taking a GPS receiver and trying to go find it and kind of having a little adventure. There's all sorts of different ways to use it. I've always liked putting this picture up here of this toad with the little GPS capture on it, because it makes me really think about the history of GPS to GPS now, and how amazing it is the way that the technology has changed, that we're able to attach this tiny little receiver to this little toad and be able to monitor everything that this toad does. And it's we're talking about a system that's only 60 years old, so pretty amazing in my mind. There's 3 segments to any GPS system: the space segment, the control segment, and the user segment. The space segment, that is the satellites out in space. The control segment is either control stations or base stations, or part of that control segment is also that Navstar base in Colorado Springs. And then your user segment is going to be the receiver. And then if you use any mapping software for the information that you get, that would also be part of the user segment. So 3 segments of the GPS system: space segment, control segment, user segment. Slide myself back up here. So, Navstar GPS, they're at about almost 13,000 miles above the Earth, and they orbit every 12 hours. They are not geostationary, so they are constantly moving. Now, in order to move around in space and in order to stay in that constant orbit, they're actually moving extremely fast. Probably somewhere in the 17,000 mile range per hour. That's about how fast those satellites are going in space. There are 31 satellites. Given the rotation of the Earth, satellites repeat exact ground tracks once a day. That's the goal. There are 6 orbital planes. So if you look at this graphic on the right here, these red lines, they represent the 6 orbital planes that are available for the satellites. And the reason that they set up 6 orbital planes with at least 4 satellites on each orbital plane was so that you could get good satellite coverage for anywhere in the world. Because the idea is, the whole point of GPS is, I want to know where I am at any part of the day. And the system is going to work off of triangulation, which we'll talk about in a little bit. But you need satellites in different places at different angles in order to be able to get the best version of your location. And so the other part of the 6 orbital planes is, you don't want just satellites going all over the place in any direction that they want, because you don't want them banging into each other. So you set it up to where If you know where the satellites are going to be, and you know that it's going to be on a consistent track, then you can set up these different tracks and then make sure none of these satellites are ever running into each other. The great benefit of doing the system this way is that you get at least 6 satellites within line of sight from almost anywhere on Earth all the time, which is, that gets to the idea of, this is why we want GPS, because we want to be able to find out where we are anytime we can. Here's a good look at those 6 orbital planes, and then the satellites, the GPS satellites that are orbiting. So just kind of a look at what that looks like, and then the 6 orbital planes with different satellites moving at about 17,000 miles an hour, 13,000 miles above the Earth. Really impressive when you think about it. So these satellites, so each PRN, pseudo-random noise, each satellite has a PRN number, a pseudo-random noise number, which codes the signal. The GPS receivers call satellites SVs or space vehicles sometimes. More than likely with the basic receivers that you get, they'll just say satellites. And the satellite just transmits radio waves to Earth. So each satellite, or each signal, contains the orbital elements, the clock behavior, the system time, and the status. An almanac is also transmitted, which will provide the data for the active satellite in the system. So it's basically, it helps the satellite find the other satellite signals as well. So lots of information being transmitted at all times from these satellites. So let's break it down and let's make it more obvious. So 3 basic pieces of information that a GPS satellite is going to transmit. An ephemeris, which is its own location. The almanac, which is the approximate location of the other satellites to it, so precision of the satellites. And then a time signal, and that's going to help enable triangulation of the position. So an ephemeris, an almanac, a time signal, or its location, its precision in terms of the other satellites, and then the time signal so that we're able to triangulate a location. So the satellite clocks. Oh, sorry. There we go. So each GPS satellite has 4 atomic clocks on it. Atomic clocks rely on the natural resonance of atoms to provide a steady tick. The master clock right now runs off of cesium. It's determining true time is really hard and very complicated, super math heavy. But it basically comes down to this. 1 second is defined as 9,192,631,770 cycles of microwave light absorbed or emitted by the hyperfine transition of cesium-133 atoms in their ground state undisturbed by external fields. That is what is happening to figure out 1 second on these super accurate atomic clocks. And this is a look at the master cesium atomic clock at the National Institute of Standards and Technology in Boulder. So if you've ever wondered about time and how time is calculated, it is extremely complicated. It's kind of amazing to me, to be honest. A little more information. There we go. So atomic clocks are incredibly precise, but not perfect. And that's just because, you've got satellites moving around at these incredible speeds. You've got things that can interfere. You got orbital instability. So all that could cause problems. However, these clocks are actually pretty stable. So it's estimated it would take an atomic clock 32,000 years to lose 1 second at a time, and the satellite will give up way before that 32,000 years of that atomic clock gives up. So actually a very stable, very consistent way to tell time. The clocks are frequently adjusted, or they're adjusted to clocks used in the ground control stations. The control is really going to be, it's just kind of the fine tuning of the satellite and space segment. There can be slight variations in clock times because of the signal speed and transmission. That's why every once in a while you'll get a slight inaccurate position, but most of the time it can correct later. And then the big thing is the GPS receiver clock and the satellite clock need to be synchronized in order to give you the most accurate location. So every once in a while your location will be off, but the receiver will sync up with the satellite's clock again, and then your location will be good. So that's the big thing, though, because the location is your location, and the distance is going to be based on the time between the signal from the satellite and your receiver. So if that time is linked up, you get an accurate location. If there's any variation in that time, you get a less accurate location. So control stations and base stations. So this is your control segment of the system. The control stations, specifically ground-based facilities that monitor and control satellite movement operated by the U.S. government. So the Navstar base in Colorado, the Shriver Air Force Base that manages the system, that is a control station. There are other ones. The Shriver Air Base is the master control station. Your base stations, though, are not associated with control stations. These are transitory. You can move them place to place. Usually you install them at locations that have been surveyed to a very high level of accuracy. So we talked about having those monuments on the ground that show a location. Usually if it's something like that that's been surveyed and we know for sure that is exactly where that point is, that's the type of place you'd set up a base station so that you could then check out what the GPS signal is and see, do we get that same location? And then that way you can really make sure to pinpoint what the error is that you might have and be able to try and reduce the error as much as possible. And so here's an example of using a GPS base station. So you've got these satellites up here, and then you would set up your base station. So there'd be a GPS receiver, a radio antenna, and then basically you've got your base station set up, and then you might set up an unknown point too, and then you just try and check, and you say, all right, so if this is a known point, I know for sure this is exactly where that point is, and I know my amount of error, then when I set up this point, I'll be able to figure it out and be able to understand what this point is because of my knowing this point. That's basically how a base station is going to work. It's your correction. It helps you just really figure out your amount of error, and then hopefully be able to reduce it, or if not, just be able to understand it so that you can give as accurate of a location as possible. If you use one of the just handheld receivers, like the ones we have at school are the Garmin eTrex 20s, you'll see when you bring up the satellite screen that you'll see it might say D when you're looking at the strength of the satellites, and that D means differential correction, and it just means that there has been this process of basically trying to improve the signal. That's this idea of differential correction, where they've done extra work to try and make sure that you're getting a more accurate location. So the GPS receiver here on the right are some examples of them. I've used a Trimble, I've used this Garmin 60CX, and at my old school we used to actually have these ones. This is a very old version of a Garmin eTrex, but the size is similar to what we have at school. And then just kind of going over how does the receiver work. So it's going to work off of triangulation. So you want to get at least 3 satellites, but preferably 4 if you're trying to do anything with elevation involved. And it's kind of a basic 4-step process. Each satellite will broadcast signals with their location, status, and precise time information, or their ephemeris, almanac, and time location. The radio signal will travel at the speed of light, and then the GPS device will receive that radio signal. It'll note its exact time of arrival, and then it'll use that to calculate the distance from the satellites, and then that will help it triangulate the location. And so it's just going to use basic geometry to determine that exact location. So I've mentioned triangulation a couple times, so let's talk about triangulation. So the location just depends on triangulation. So to understand the horizontal position, you need 3 signal distances from the orbiting satellites. The receiver will calculate how long each signal took in conjunction with the almanac to determine the distance to each satellite. And because you figured out the distance to each satellite from the location, you're able to precisely get the location. Because rather than just saying, here's the signal from one satellite, that could be off. But if you get different satellites from all these different angles telling you this is exactly where your location is, the better off you're going to be. Now, the other thing is it takes a minimum of 3 satellites to do this. But what you'll see is if it's a good time of the day and you've got nothing in the way, you might have 20 of those satellites, or 10, or 15. And the more you get a signal from a satellite saying, this is your location, and this is your location, and this is your location, the more it's going to make it easier to find that exact location. And then just going back to something I mentioned earlier as well, a 4th signal is needed if you want to get elevation. But if you have anything more than 4, elevation and location, the more signals you have better. Hardly ever will you get 31. It'd be pretty amazing if you were in some sort of location where all the satellites that are focusing on the whole world you'd be able to pick up a signal from them. But there are places where you can get quite a bit of the satellites to pick up. So just another look at the whole system. So number 1 here, tracking stations use radio to determine the orbits of the GPS satellites. The command center will transmit orbital data, time corrections, and locations of other satellites in the GPS constellation. The GPS satellites simultaneously transmit synchronized time and orbital data back to Earth. The GPS receivers compute the location using the orbital data and the difference in arrival times of the signals for at least the 4 satellites, and the whole system works together all the way from Schreiber for space to the satellites, all the way to whatever location you're at, and gives you a signal in your receiver. So what can be problematic in terms of using a GPS? Atmospheric interference is a big deal. So your atmospheric interference is least when the satellite is directly overhead. And so what that means is, think about the idea of up. If you're outside and you're trying to get a GPS signal, if the satellite is directly above you with nothing in the way, that's going to be the easiest way to get that signal. But if the satellite is all the way out on the horizon in either direction or off at some weird angle, there could be all sorts of other things that get in the way in terms of what's out there in the atmosphere, space dust, and other satellites and other things flying around in the atmosphere. So it's important to just think of the idea that straight up would be the easiest way to get a signal. Ephemeris, it's only valid for about 4 hours. If the satellite isn't where it was suggested to be in the almanac, it will cause location determination. So just making sure that the ephemeris, the position, it's only good for a little bit because those things are moving so fast. You could get atomic clock errors. Mostly it be in the signal relay of the error, not in the clock itself. And then your GPS receiver's clock. So every once in a while it won't be synced up with every single satellite because of all these other things going on. And more likely, this is much more likely to happen as a source of error than the atomic clock error. For you though, these last three are the ones that I'd say are really the most important sources of error, because they're really the ones that we can actually do something about. So signal to noise ratio. So satellite signals do not penetrate buildings or trees. So really try and stay away from objects, especially any object that's going to be overhead, because that's where our best source of signal is going to be. Multipath error. And multipath is the signal bouncing off of landscape features. So just here's an example right here. If I was standing right here in the middle of this this big combine and this house, and I'm trying to get a GPS signal, and then the satellite is sending a signal, but it's bouncing off of this building and it's bouncing off of the combine, and then I'm trying to get it. It's very possible I get kind of a garbled signal or a not as accurate signal. And then shadowing. So the idea of the signal being reduced in forested conditions, basically having so many different objects and so many other things in the way to make sure that there's not a good signal. Now, the big thing to think about is if you're in heavy forested conditions and you cannot do anything about this, you just have to understand that you're gonna be dealing with error, and so you really just kind of want to plan for that. Like for instance, if I'm down in a valley that's in the shadow of a mountain or hill, and I know that there's going to be that's going to interfere with the signal, especially at the time of day where the satellites might be, I really want to just think about, okay, my locations might not be as accurate as I want them to be, so I just have to think about, all right, well, if that's the case, then if I'm trying to walk to this specific point, I'll walk there, but I'm going to have to assume that once I get to where the GPS tells me, it might be somewhere within that 20 feet or 30 feet, and I might have to do some looking around. So it's just important to understand that, to just avoid frustration. So just some important points with the GPS. Horizontal GPS positions typically are 2 to 5 times more accurate than vertical positions. So in terms of your elevation, so distance is much easier for GPS to calculate rather than elevation. Elevation is a little bit harder, but we kind of have really, most of you have probably used Google Maps or Waze or Apple Maps for quite a bit of time. So distance, we've kind of nailed that one, but elevation is still a little bit trickier. The multipath error that we spoke of, that one is the largest source of inaccuracy in natural resources due to dense vegetation or severe topographical relief, or just basically lots of trees and lots of plants for the signal to bounce off of, especially if it's taller than us or the receiver that we're holding, and then topographical relief. If we're in mountains and lots of up and down, or we're in valleys or saddles, might get really hard to get a signal. Here's just an idea of those sources of error, and how much you can see how much worse of a problem multipath is as opposed to some of the other stuff. So, some important questions. Whoops. When is the best time to collect data? It varies by satellite position and time of day. The best thing is to just kind of try it a bunch of times, and you'll just kind of start getting used to which satellites are going to be around at which times. How much data do I need to collect? Really just think about, most of the time you're just going to need to take a receiver out there and just go and get data, but you really want to just think about your project, how much work is involved, how long is it going to take, and how accurate do you need it to be? Because if you need it to be really accurate, maybe you need to set up base stations and go through all of that. If it's okay that it's somewhere around there and we can figure it out, you don't need to spend as much time. So just how accurate do you need to be? Do I need to differentially correct data? It's probably needed. So just when you look at the receiver you're using, if you can get that differentially corrected data, if you can get the D on there, you're great. If it's not available, then maybe the place you're working at needs to invest in base stations and learn how to go through that process. Will the base station have data covering my time period? The base stations don't collect data continuously, so you kind of just have to go off of whatever base station you're using and figure out how to best use it. Do I need to remove multipath error? If you can, great. You might have to delete some points that are just terrible, but really it's much more of an idea of how do you reduce it than how do you get rid of it. And then will GPS data be integrated with other GIS data? Absolutely, but you just need to know how to do that process, and we'll talk about that with GIS labs and classes. And that's it. So hopefully that's just a quick overview of GPS, and then we'll get as close to hands-on as we can with the lab.